The only thing that I'm trying to ensure is that there is no clash with your other classes, right? So I'm just looking at the timetable, but by the end of today, I'll inform these timings to you. And so I will also indicate how many people can sign up for each one of the sessions, which will be like typically hour and a half or 3 hours. I mean, depending on the time. So I mean, what I mean is that I would like you to take care of setting up the Google Forms and you know uh, just the administrative part. Okay.
Yes.
And you can do that on a first come first serve basis. If there are any conflicts, then you can try to resolve. um, yeah, one more thing, by the way. So I said that this is during the week of so not this week, not the following week, but the week after that. Okay. That is because I wanted to keep my promise and give you enough advance notice. But if anybody wants to have this exam earlier, for example, the weekend before the weekend before the Saturday and Sunday before that Monday, I'm perfectly okay. It's just that I want to give everybody the chance to do the homeworks completely and also to write the quizzes. If you require that in order to sort of sharpen your mind, or to have that as a deadline to make you focus. But if somebody wants to have this exam out of the way earlier, I have absolutely no problem. Okay, so we are still um, just about maybe 2/3 of the class.
Hello, sir.
Yes.
Sir, what will be the mode of the quizzes that will be taken during the
Yeah,
class?
so it will be so basically I will have you up. I haven't completely decided whether I want to make something on Moodle, but the default thing will be that I will give you the questions, I will display them on the board or send you the document, and you will just solve them and upload your answers.
Okay, sir.
So you can either do on. So I hope that Moodle is okay for everybody, but if not, then we can have then we can maybe have even it's submitted by WhatsApp to the TAs. We can sort that out. I'll discuss with the TAs and I'll sort that out. Other questions or anything? Hello.
So that example thing that you mentioned you'll be doing, like in the last class, which we didn't have.
Uh, right. So yeah, what about the last class?
I mean, the class that we didn't have last Monday. which you mentioned we might have.
Right. Yeah, I basically asked you whether you want to have a class, and then we decided that that would be too stressful. So, right, what about it?
So I was asking if you'll be doing that material like today or later.
Uh, well, I mean, I will just incorporate that in the next classes. So, today I was today I really just wanted to do a little bit of review of where we are, um, and just sketch a couple of things and ask you to do the proofs. Uh,
Okay, so thank
okay, but we will do those examples. So you see, so one of the things that we said is that whatever you did last semester for differentiation, we want to do in one variable. You want to do the same things this semester, this time for multiple variables. And okay, so let's just get started. We're just having a sort of freewheeling discussion. Um, so, um, so sequences, convergence of sequences, we did that. Functions, limits of functions, continuity. We did that for functions between some subset of Rm to Rn. We did that. And generally speaking, we defined this for metric spaces. Right? So that's a natural language in terms of which to do this. For topology, what we did is a somewhat um, not non-standard. Everything is very standard. But there is some choice about, do you do this only for Rn, only for subsets of Rn, or do you do it in general for non-linear spaces in that language, or do you do it for metric spaces or for topological spaces? And the way I did this is that whatever was the concept, whatever was the natural setting for that, I defined the concept in that setting. Okay, so that was the topology part. Then for derivatives, what were the key things? Definition of the derivative. Okay, so I think maybe I should just start writing this down. And I also have to write down about the mistake that I made last time. So, okay. So for today's class, I really do not have anything big planned. Okay, just wanted to have a discussion. So if anybody just wants to chime in with something, then just feel free to go ahead. Okay. So it's just a discussion class, really. Um, so what were the key definitions and results? I'll not write down, but one was non-linear spaces. What was the key result for this? Okay, I think I should start recording also. Though today's lecture, it's not clear what value it has in recording it, but anyway. So
recording in progress.
yeah, so about non-linear spaces, what was the key result?
The topology generated by all norms are equal on finite dimensional vectors.
Right. And the reason for that was, so there is something stronger than just the topologies being equal. What is the reason why all topologies are the same? Coming from any norm on a finite dimensional vector space.
Intuitively, it's because we can put balls inside the balls generated by other.
Correct. So what is the technical word for saying what you're
compactness.
saying? I'm sorry, say that again, please.
Compactness. I think field definitive.
But you see, putting balls inside balls, I mean, those balls are open balls. No? So I'm just looking for a definition here. What is the thing that I can put ball, given any ball, I can put a ball under norm inside that and vice versa. What does that mean?
Equivalence.
Yeah, so right, so all norms on a finite dimensional vector space are equivalent. Okay, so And what was the key reason behind this?
Compactness of unit bond.
Right. So compact, see, or rather the characterization of compactness. We had Heine-Borel, right? That is a key result here. And specifically, what was it that, what consequence of Heine-Borel did we use over here? This is something to do with functions. So we said that the norm function on any non-linear space, any norm function actually, is continuous. And how did Heine-Borel then help us? What do we know about continuous functions defined on compact sets?
Images are compact.
Right. And if the image, and if it is a real valued function, then what do we know?
The open set is closed and bounded. The image is closed and bounded in R.
Right. So in particular, just look back at analysis 1. If I have a function defined on a compact, continuous function defined on a compact set, then what can I say about the values that it takes on that compact set? Yeah, so you're saying the values are closed and bounded. In particular, this function is bounded, so it will have a supremum and an infimum, and moreover, this supremum and infimum will actually be achieved, right? So that was okay. So non-linear spaces, and the result was they're all equivalent. But really, then we define metric spaces and topology metric spaces. And then we had this discussion of continuity. So let's see, can talk about, so for metric spaces, so I will just say this one. Can talk about sequences, convergence, limits of functions, and continuity. Okay. So one of the key things, for example, is that if I have a function from some metric space to Rn, then what was a very useful thing to, something that we used again and again, a simple thing, but a useful thing was that to evaluate the limit of a sequence of things in Rn, or to evaluate or to check, to calculate the limit of a function that is Rn valued at some point, or to test the continuity of a function that is Rn valued at some point, what is necessary and, more interestingly, sufficient?
If we split the function into components,
Right.
each of the things have to converge.
Correct. So component wise, right? And remember, for this to have this L infinity norm, the max norm was useful. Okay. But anyway, so we had this. So that was okay. So this was about topology, and then about derivatives. So we can sort of see this in steps, right? So derivative of function from R to R, that was last semester. And what is the next step, which really is just one step? I mean, there is nothing much to say. If I have a function from R to Rn, this is a vector valued function, right? Then here I can really use the same definition of the derivative. It's just that the values will take place in a vector, but if I calculate f of a plus whatever, x plus h, then that makes sense. I mean, because the arguments are all real numbers, and I can divide by h, that's also a real number. So there is no, this is very similar. So extends easily to okay. But then if I have a function the other way, which is Rm to R, then what we saw was there was the notion of, before we make the jump to the full derivative, there was this notion of partial derivatives, which is when I fix just all but one of the coordinates and just regard it as a function of one variable. And then a slightly more general version of this, you do not have to fix a direction that has to be along one of the coordinates. You can fix a direction which is along any one of the lines. And then what do we call it?
Directional derivative.
Directional derivatives. Directional derivative along some v, along some, okay, this is too illegible. Yeah, so the only thing is directional derivative is fine. So you can just recall the definition for yourself more generally. Okay, so let's call this vector, okay, v in Rn. So what was that? F prime of, okay, F prime at some point A. No, actually not F prime. I'm still calculating the directional derivative. So d sub v of f of at A is equal to limit as what? H approaches 0. Okay, so tell me f of, come on,
A plus V HV.
A plus HV, and then you do exactly the same thing, f of minus f of A divided by H, right? Okay, so the only thing is one small point to say over here, which is, you see, when we think of a direction, the direction of V and the direction of 2V, are they the same directions?
Yes.
Right, so you see, it depends on sort of what we mean by a direction, correct? So if I'm calling this directional derivative along V, if I use V here versus if I use 2V here, will I get the same answer from this limit?
No, you won't.
No, in fact, what will be the, so just a small remark over here. D of, in the direction lambda V of f of A and dv of f at A, what will be the connection between them? Just reparameterize and see what you will get.
Mod lambdas.
So I'm going to get lambda times that, correct? I hope I got that right. Yes? Sorry, is that right?
Yes.
Okay. But really, if so, usually if I want, so usually, so, or maybe often, we take, if I'm really interested in the direction, often I take the unit vector in that direction for normalize the vector. Okay, but anyway, so this is all okay. The thing is f prime of A for, so this is a new definition for f from open U in Rm to Rn is a linear map. T from, and A is a point in here, such that a certain limit is 0, right? I will not write down that limit. But it's a linear map. And what does this linear map have to do with directional derivatives or partial derivatives?
The linear map, the value of that linear map on the unit vector will give you the directional derivative corresponding to that unit vector.
What about partial derivatives? Partial derivatives, I remember, only just real, only, so partial derivatives of component functions. So f itself, it will be a collection of n functions, right? N real valued functions. Sorry, not a collection, a list of n real valued functions, f1 up to fn, and each one of these functions is a function of m variables. So I'm going to have m times n partial derivatives, and what we saw was that if the total derivative exists, f prime of a, then all the partial derivatives exist, and their matrix is precisely the matrix of this linear map. What about the converse? Such that certain limit. Okay, so in fact, let's just write this down. So while I write down this limit, you can tell me about the converse. Such that limit as h approaches 0 of f of a plus h minus f of a minus what? So let's write down the same definition, divided by h. So that should be equal to f prime of a, but f prime of a is a linear map. So I get to put that linear map here, t. So how do I need to modify this? Come on, this should really not be, I'm doing this only because there has been a long gap, but really all of this should be instantaneous.
We need mod h in the denominator.
So we need mod h in the denominator because h is a vector here in the source. Okay. And on the numerator?
We apply h to t, and we can leave it like that, or we can take norm.
Right. So notice what I've written here is semantic nonsense. F of a plus h and f of a, they are both vectors in Rn. T is a linear map. So I need to apply it to something, and I will apply it to h. And this should be 0. And I can equivalently put norm on the top. In that case, on the right hand side, I will not have the 0 vector, but the 0 scalar. Okay. So all partial derivatives exist and make up the matrix of f prime of a with respect to standard bases. How about the converse? Is that true?
No, sir.
No. But when is the converse true?
If the partial derivatives exist in an open set and if they are continuous.
Correct. So this is false, but it is true. And that was the characterization of C1 functions that we had last time. Okay. So, so let's write down that the converse is true if all continues only at that point, or what?
Continuous in the open set.
So really, and what you should do is this is a very nice proof. It is really worth understanding the proof properly. So what was the key ingredient in the proof?
We took a step-by-step approximation.
We took a step-by-step approach, and on each step, what did I use?
That the difference is small.
Right, but what was the technical ingredient?
Like mean value theorem of one variable.
Right. Yeah, exactly, right. So if all partial derivatives are continuous in some neighborhood, and so what was really used was the mean value theorem. And again, remember f prime of a existing also gave me something else, right? So what is the converse? So suppose that the function f is defined on an open set. u to Rn, and such that all the partial derivatives exist at every point in that open set and are continuous. What is the conclusion? Do we only know that f prime of A exists?
Yeah, it is also continuous.
It is also continuous. And why is that? Is that hard?
Like each of the components are continuous.
Exactly. So you see, the continuity is simple. This was the thing that we said earlier, right? The checking continuity of a function into Rn, you just have to check that each one of the components is continuous. If the partial derivatives are continuous on U, and in that case, f prime. Okay. So good point. So what are we saying? Are we saying that f prime of A is continuous, or are we saying that f prime is continuous?
F prime is continuous.
Okay. Is f prime of A continuous? Does
Yes,
that
sir.
even make sense?
Yes, sir. It is continuous because it's a linear function.
Right. So it doesn't. So f prime of A, if it exists, it's a linear map. Linear map between two vector spaces is continuous. Right. So f prime of A, when it exists, is always a continuous map. But here, what we are saying is that f prime as a map is continuous. So f prime is a map from where to where?
R power m to R power nm.
As a map. Actually, so it is not from R power m because,
U.
right. So as a map from U to the space of linear maps from Rm to Rn. So this is isomorphic to Rmn, if I think of this as a tuple of mn numbers. But really speaking, it's the space of linear operators. So if I think of it as Rmn, then of course, I mean, it's a Euclidean space. I mean, but what is the topology that I usually give to this vector space when I regard it as space of linear maps from one vector space to another? I give it the topology that comes from a norm. But which norm do I use here?
All norms are equivalent.
All norms are equivalent. So that's a very relevant observation. So it doesn't really matter for continuity. But in order to carry out, which is the norm that is useful for estimations?
Operator norm.
It's the operator norm that is useful. Okay. So good. All right. Yeah. So this was okay. And so key was key in proof. One variable mean value theorem, and if not for anything else, to sort of atone for my sins, let us state this result, because I got completely confused with this. So which says what? Which states if g is a function from a closed interval to real numbers such that g is continuous and g prime exists on, then what happens? Okay, I'll just write it down. There exists C. Where does this C exist? In open interval AB, such that f prime of C is f of B minus f of A divided by B minus A, correct? Okay, so the reason why I stated it is because last time I thought that, or I stated emphatically that this G prime needs to be continuous, which is not the case. And the reason why I got confused is because the continuity of the derivative or continuity of the partial derivatives was something that was required for characterizing the previous, for characterizing when f prime exists based on existence of partial derivatives, right? So I got confused and I made that wrong statement. Okay, so very good. So then we also saw chain rule for multivariable situations. And the chain rule becomes nice here. What does it say? Remember, the derivative is a linear map. So what does the chain rule say? Derivative of a composite is
It's kind of the composite of the derivatives. It's g prime of fa composed with f prime of a.
yeah, but why are you saying kind of? It really is exactly the composite. No?
Right. I said kind of because they're at different points, but yeah, it really is.
Right. But you see, now here is the thing. When I calculate the derivative at a point A, the point A is not part of the source of that map.
Yeah, yeah.
Right? Okay, so psychologically, this is sort of a useful thing to keep in mind, even for one variable case. See, when I calculate the derivative of x square at, let's say, x equal to 3, then I get the number 6. That number 6, regarded as a map, is a map from R to R, which takes any value t to 6 times t. Now, the way we visualize it is that we visualize this line sitting at the point whatever 3,9 on the graph of the original function. But the point 3 is not part of the domain of the derivative function, right?
Yes, sir. Yeah.
Right. Okay. So so if you want to sort of put all of these things together, then I mean, okay, we will talk maybe more about this when we talk about tangent spaces. Okay, so anyway, we saw chain rule, which really says that derivative of composite is composition of derivative. Composition is composition. See if I can get the spelling right. Composition of derivatives. Of course, provided those individual derivatives exist, right? Okay. So then what were some other things? So we saw the mean value theorem. There were two versions of the mean value theorem that we saw. And we said this above, characterization of C1 functions. I already stated that. So what is a C1 function? So let's do this now. Definition. So suppose U open in Rm. So this is given. Then a function f from U to Rn is called C1 if f prime of A exists for all A in U, and maybe I can say C1 of U, and f prime is a continuous function, right? And we saw that this happens precisely when all partial derivatives exist and they're also continuous functions. Okay, very well. But the reason to write down this definition, and now is the only sort of first slightly new thing that I'm doing, is that I can now iterate. Okay, so what I want to do is I want to define higher derivatives. Okay, let's back up for a moment. And so now I want to define and class ck of functions for values of k that are bigger than 1, but actually we can say greater than or equal to 0. Okay, so let's back up for a moment. Higher derivatives. Why do you want to define higher derivatives? I mean, we can, of course, in math, what you can do, and is interesting, you do. But where do higher derivatives come up? How are they useful?
Taylor's theorem.
Taylor's theorem, right? So that is one thing. Anywhere else? You see this thing.
Optimization problems.
Yeah, and the second derivative is useful, right? And so okay. So okay, so useful one to define. So like in one variable case, useful. So these are useful for Taylor approximation, Taylor's theorem, and maximization and finding maxima and minima. Okay. All right. So so very well. So first thing to do is so review this. So maxima and minima, it will take us some time because we will need to do a little bit of linear algebra for that. But Taylor's theorem, we will sort of take care of it fairly easily once the correct ingredients are in place. And for that, the one variable Taylor's theorem version you should review for next class itself. We'll get to it in the next class or two. Okay, but all right. So first thing is, if I want to talk about second derivative, then what kind of gadget is it?
It's a linear map from Rm to the space of linear maps from Rm to Rm.
Okay, so let's see here. Okay, what was so the second derivative? Let's go back. Okay, all right, 1 second. Where did we write this? Okay. So this thing that is written at the bottom here. This is what the derivative is as a this is what the derivative is as a map, not derivative at one point. Okay, the derivative at one point is a linear map from Rm to Rn. But the derivative map, which takes any point A in the open set U. So let's assume that the function f is given that is differentiable at every point. So at every point A, I have a linear operator. So I have a map from U to the space of linear maps. So what should the second derivative be? The second derivative should be the second derivative of the second derivative should be the derivative of this function. And again, first only at a point, right? So the derivative, all right. So second derivative of f from U to Rn at A in U, which is in assuming f prime exists, right? So maybe even before this should be, so this is equal to derivative at A of f prime, which is a function from U to the space of linear maps from Rm to Rn. Therefore, f double prime of A or d2f of A is a map from where to where?
U to the space of linear maps from Rm to the space of linear maps from Rm to Rm.
Okay, so remember this is the derivative of a function at a point. The derivative of a function at a point is a linear map. So can the source of this d2f of a, can it be u? No, right? So this is going to be a map from Rm to the same the same vector space as the target, right? So this is going to be a map, a linear map from Rm to the space of linear maps from Rm to Rn. All right. That's what the second derivative is going to be. Very well. Okay. There is some, there's just some sort of getting used to what is going on over here. So now a couple of questions. One is, what are the components of this? Because we said that for f prime of a, its components were all partial derivatives of all component functions in all directions. So what are the components of this? So what is the matrix of f double prime of t? So first of all, with respect to what basis? What is going to be the size of this matrix? How many rows and how many columns?
mn rows and m columns.
Right. Yeah. Because you see the image of any vector is going to have mn components. That means the number of rows is going to be mn. The number of columns is going to be m. Of course, this does a little bit of violence to what it is, because to list those m times n numbers in a single linear order sort of destroys the nature of it as itself coming from a rectangle. So maybe the way we should think of these numbers is not in a matrix, but perhaps in a rectangular box, right? If you want to arrange this. But again, if you want to think of it as a map between vector spaces, then you have to think of it as a matrix, rows and columns. Okay, matrix. So how do we write this? So let us say that f is equal to real valued functions f1 to fn. Okay. So matrix of this is going to have let's say mn rows and m columns. And what are going to be the entries? Okay.
The partial derivatives of the entries of.
So the the numerator is easy. I take the partial derivative of each one of the component functions, right? In one of the directions. Yeah. So I take partial derivatives of xi, but with respect to what? Now, what are the variables here? I'm sorry. So, oh, no. 1 second. Just got confused myself. Okay. So how many components does this function have? So I got it actually wrong. How many variables are here? The map is again from u. The map f prime is again from u. So I will take so how many directions are there? How many principal directions are there for me to take derivative with respect to?
M directions.
Right. So this is going to be Lxj, j going from 1 to m. But okay, so actually there is something to say over here, right? So maybe let me put this in quotation marks. So mn, how many functions are here? the way I really want to write this is del of not f. What is the function whose partial derivatives I am taking?
F prime.
Right? So I have to take the function f prime. And how many components does this function have? It has m times n components, right? So del f prime pq, where p goes from whatever 1 to so now it depends on how you are going to so let us say p goes from 1 to n and q goes from 1 to n. So question, can these be understood in terms of partial derivatives of f? It's a natural question, right? The partial derivatives of various fi's. What do you think? So you should think about this question. All right. To see this way. If I want to take double derivatives, then if I take a partial derivative of one of the fi's with respect to one of the original variables. So let us say I take del f1 by del x3, right? What kind of function is this? This is a function from where to where? Remember, all of these partial derivatives exist. So del f, let's say del f1 by del x3. This is a function from where to where?
From R to R.
It is a function from u, right?
Oh, yes.
Right? It's a function from u to r. I can take its partial derivatives, right? So let us say I have del f1 by del x3, and I can take del by del x2 of this. So specifically, okay, so I'm just going to use I here. So, and to make the, let's not use, let's use the operator notation. I first use, I take fi, then I calculate del by del xk of this, and then I calculate del by del xl of this. Again, I'm going to get how many numbers? Oh, sorry, this is wrong here. This should be m there. How many numbers are there? Again, of these sort of second partial derivatives. Well, I can be taken from, oh, okay, so something went off here. Let's, so yeah, so how many such possibilities are there? You see, the number of functions is the number of functions is n, and how many different partial derivatives I can take? The k and l, each one can be chosen in m ways, right? So the total number of such things that I've written in the question at the bottom of the page, how many is that?
M square n.
And the same thing for what is written in the quotation marks, it's the same number of possibilities, right? So now you should think about whether there is any connection between these two, right? So this is one thing to think about. And there is yet another question. So, question. Does the order in which I take partial derivatives matter, right? So, let's write this in words only. Which is to say, if I first take partial derivative with respect to x1 and then with respect to x2, is it really the same thing as taking it with respect to x2 and then taking the derivative of that with respect to x1, partial derivative? The answer is yes, but not always. Right? So this is again a standard thing. Answer in no, but true in good conditions. So sorry, somebody was saying something.
In case of continuously differentiable,
But yes,
but that is not the strongest.
Under good conditions. What do you think the conditions are?
Continuously differentiable implies they will come.
Sorry, so what is continuously differentiable? No, and also if you know the result, maybe other people can guess. What do you think is the result? So is it enough, for example, that, by the way, so do you think that continuity of the function f prime will be enough for this? The answer is no, you see, because when I want to take these double derivatives, it is related to actually taking the derivative of the function f prime. So f prime needs to be differentiable. Of course, it has to be continuous for us to even talk about such matters. So something more is required. The point is that if these double partial derivatives, they themselves are continuous functions, then the order does not matter. That's the result. It's a standard result, and please read the proof of this. So we will do this next time. Yes, under good conditions.
If the double partial derivatives are continuous, will that imply that it is totally differentiable?
Good question. So I don't know the answer to that, but we will discuss this next time. Okay.
Sir, 1 minute, can you repeat that condition once more?
Okay. So under good conditions, namely when, okay, so let me not state it because I have not set up the terminology also. Let us say that if I apply both the partial derivatives and that operation, namely taking del by del x, k of del by del x, L of whatever function, right? Suppose that operation results in a continuous. So suppose that operation is, after applying to f, gives me a continuous function. Okay. In that case, in fact, what it will say is that in that case, the other order actually also can be defined, and the two will be equal. So if instead of k and l, let me just call them 1 and 2. So this way, if I apply d1 and then d2 to f, and if the resulting thing does exist and it's continuous, then d2 applied to d1 applied to f is also exists, and the two of them will be equal. That's the result, which we will prove next time. This is an application again of our workhorse result. You see, the mean value theorem, the one variable mean value theorem is a very versatile result. You use it in many different ways, which is what we will use in order to prove this result. So we will prove this. So read this. So statement and proof next time. But okay, anyway, so let's go back to, so this was, so two questions, right? So one was the matrix of f double prime. So this is something or the other about partial derivatives, right? But now the next question is two. F double prime, suppose f double prime, if f double prime A exists for all A in U, then I get a function f double prime or d2f. This is a function from where to where? No? Remember, f double prime of A is a linear map. It goes from Rm to the space of linear maps. But now this becomes a little more mind-bending. F double prime itself is a function from where to where. For every A, what am I getting? For every A, I'm getting f double prime of A. So let's write this down. So this sends A to f double prime of A. So what kind of animal is A? Well, it's an element of the open set U in Rm. But what is f double prime of A? What kind of animal is that? Well, let's look back up. What is f double prime of A? It is a linear map from Rm to the space of linear maps from Rm to Rn. That means f double prime of A is a denizen of the world of linear maps from a vector space to the linear maps between two other vector spaces. So on the right hand side, what should I write? Remember this L notation. LVW is the space of all linear maps from V to W. So being the derivative, so what do I get? F double prime of A is in the space of linear maps from where to where?
Rm to LRM Rm.
Right, exactly. Okay, so very good. So that is f double prime of A. And now you see we can keep playing the game. F double prime is a function. The target space looks a little complicated, right? But it is just a vector space. What is the dimension of that vector space?
M square n.
M square n, but it is a vector space. As such, so RHS is a vector space of dimension m square n. So in particular, it has a topology, standard topology. So I can ask about continuity of the function f double prime. Okay, so with this we can make a definition. So definition. So C1, so U is an open set in R M. And let us just say that f is a function from U to, let's just say R, okay? Because whatever I define, whatever property I define, continuity, differentiability, double differentiability, whatever, to check it for a multi-valued function, it's the same thing as checking for each component, right? So, okay, we can even say Rn. N is equal to 1 is also okay, right? So f is C naught if f is C1 if f prime A exists for all a in U, and f prime is continuous. So I don't want to say that it is only one differentiable once. The nice condition was that f prime is itself continuous, right? Because then that could be characterized in terms of partial derivatives and their continuity. Okay. So what do you think is f? What should I call SC2?
Second derivative exists.
That means that f double prime A exists for all a in U, and f double prime is a continuous function. From where to where? What is written up there, right? This is a continuous function from U to a vector space that has dimension m square n. Okay. And then you continue in this fashion. So on f is ck if that is, which is to say, i.e. f is k times differentiable on U, and the kth derivative is a continuous function. Okay, so let's just go back. What do you think f should be? What do you think C0 should be defined? What does it mean that f is in the C0 class, or f is a C0 function? Right. So what it says is that we'll just blindly apply the definition, and you see what it says. So f1, if I put 1, that means take the derivative 1 times. F double prime means take the derivative 2 times. So f0 means take the derivative no times, and that means the function itself, right? So what it says is that f is 0 times differentiable. That means no condition at all. But the result of doing that differentiation should give me a continuous function, right? So it works out. Yes. So I mean, just as a terminology, it works out perfectly if f is continuous. So those are the classes of functions: f continuous, continuously differentiable, continuously double differentiable, and so on. Right? Okay. So this is really just sort of semantics. But the C1 case tells us that this is a nice class to consider. So the questions that I'm leaving for you to do, let me just put them in sort of color boxes. I want to do. So this matrix of f double prime of a. So this question and this question. Understanding higher derivatives in terms of partial derivatives. Okay, so that is one question. The second question is what I said about so we are almost out of time. Let me just end with what can we do usefully in a couple of minutes. Okay, so Taylor's theorem, I was going to get you to state Taylor's theorem, but it will take up some time to set up the terminology. So let me just ask you, what is the base case of Taylor's theorem? Where does it start? What is the first case of Taylor's theorem?
The standard mean value theorem.
Yeah, exactly. So you see, it's the mean value theorem is really at the foundation. So you just build on that, correct? And so we have mean value theorem in multivariable situation also, and the one variable mean value theorem. So see the proof of mean value theorem. And in fact, Rudin does not even do this in his text. He leaves this as an exercise. So try to do this. Let me just end with sort of one thing over here. This is more in the direction of linear algebra. You see, this thing over here looks like a complicated gadget, right? the space of linear maps from some vector space, but whose target is also the space of linear maps. So let's see this a little bit. And so this is now extra. So maybe we should end the class here. I'll just sort of end this with a question, which I will then discuss afterwards, but I'll let you go after stating this question. See, this is a space of linear maps from Rm to the space of linear maps from Rm to Rn. Is there a way to describe this map, a map that belongs to this space? Is there a way to describe this in a simpler way or an alternative way? Okay, so that is the question. And I'll leave you to think about this, or you can stick around and we'll discuss it some more.
Recording stopped.
What is the question again?
Sorry, say that again, please.
Can you say the question again?
Okay, so the question is, I'll now write this. L V U W for where are vector spaces. It's a complicated looking thing, no? So how do I understand this? And so the first thing, just said theoretically. Just said theoretically, if A, B, C are sets, then the set of maps from A to the set of. So I'm simply forgetting linearity. I'm simply regarding a map. I'm simply regarding an element of the given set as a map from A to the set of maps from B to C. But this is kind of a rather simple thing. So I'm simply going to say that this is the same as. So this is in quotation marks. Is the same as, of course, under some kind of dictionary. Now, one of the key things in mathematics is when two different things can be regarded as the same. Right? Same for the purpose at hand. Okay. So what does it mean that for every element small a, I get a map? Right. So let us say there is some map f here. So what does f do? That is, f of a is a map from B to C. For every a, I'm getting a map from B to C. For every a, so when you see this, it is completely obvious. But the first time you see this, you may have to think about this a little bit. And really, maybe the easy direction is from right to left. Okay. So suppose I have a map here, right? So let's call this map alpha.
A comma B plus.
Right. So suppose alpha is a map. So what does alpha do? Alpha of B, alpha of, alpha of A, or let's not call it alpha. Alpha is bad. Let's call it phi. So let us suppose phi is such a map, right? So phi of A comma B is some element of C, correct? If that is the case, then what does that correspond to? What f does it correspond to? What should f of A be? F of A is the map from B to C. What does it do? Where does it send small b to?
small c.
Exactly. So it's really sends it to, or let's just call this phi of a comma b. In computer science or logic, they call this currying. So this is really just language, nothing else. See, giving a map from A cross B to C, what does it mean? If I fix what is in the first slot, then that means for every element B, then I'm getting a C, right? That's exactly what it is saying. Giving a map from a Cartesian product, if I look at this map by fixing any element of the set capital A at a time, then for every A, I'm getting a function from B to C. For every small a, I'm getting a function from capital B to capital C. That's exactly what I have written on the left-hand side. And you can see that this is a dictionary. Okay. So the question is, under this dictionary, maps in L, V, L, U, W. There are now two linearity conditions given, right? The map from V to the maps from U to W itself is a linear map. But the target of this is also has to be in the linear maps. Actually, I should have said the second thing first. For every V, the map that I get from U to W is required to be a linear map, not just any old map. And not only that, this assignment from V to a linear map, that also needs to be linear. So you see there are two conditions correspond to. So must correspond to some special kinds of maps. Maps from V cross U to W. So that's what it is, no? What kind of maps? And if you have seen the answer, then you should not say it. If you have not seen the answer, then I should say that it is a fairly easy thing. The answer is something that when you write it down, it will make itself, it is a notion that you have seen. Okay, so the answer is sort of just like one phrase answer, but it is worthwhile to work it out for yourself. It's an exercise. First, in the exercise is the difficulty of this exercise, if any, is not in doing it, but just in getting comfortable with the notions. Right. Okay, so that's really all that I wanted to say for today. Let me ask you one more thing, which is, in my mail, I said that we need some amount of linear algebra, and that is part of the official syllabus also, which is review of inner product spaces. And in particular, we need to be able to diagonalize symmetric matrices. Right? The symmetric matrix is going to come because the partial derivatives are going to have a symmetry property. Right? And being able to diagonalize matrices is always a great thing. So, but I'm given to understand that a considerable amount of your Algebra 2 course this semester was done on linear algebra. So what I would like to know is how much was done. Did you do spectral theorem?
Yes, sir.
Okay. So you talked about positive definite. So you talked about bilinear forms. Yeah.
Yes, sir. Yeah.
Hermitian forms.
Yeah.
Okay. Positive definite.
Yeah.
Okay. How about orthogonal matrices and unitary matrices?
Yeah.
Yes. Okay. And then you also did the diagonalization theorem.
Spectral theorem for normal operators.
Oh, for normal operators. Okay. All right. Very good. So you must have done Gram-Schmidt maybe earlier in the first semester itself.
Yeah.
Right. Okay. Excellent. So, okay. I mean, that just frees up a fair amount of time for us. I can still try to do a review, which is what is required only for our purposes.
Sir, will we need tensor products?
No, we don't.
Okay.
We don't need tensor products. So Of course, tensor product is something that one should just know. The first time you
Also
see
tensor that is LV comma LQ.
sorry, say that again, please.
Is this also a sort of tensor of length? LV?
I mean, so what we did in this question, tensor products are involved over here. You see, tensor product has to do with really bilinear maps. So when you said bilinear forms, you were already sort of knocking at the door over there. But again, there is absolutely no need to have tensor product. So I will not make it a requirement for this course, but we can discuss it at some point if you want.
Yes, sir. Like,
but as an extra thing, or maybe at the end.
okay, sir.
So yeah, just give me a moment, please. But again, so are the class reps there? Maybe what I see, the point is, if there are people who would like me to review linear algebra, even from basics, and even if it is 5 people or even less, I'm perfectly happy to do that, right? If it is something like 15 people, then I'm happy to do it in class, at least a condensed development. If it is smaller, then I'm happy to do it outside. But I do need to get some instruction from you about this. So maybe you can conduct a survey, or maybe I will conduct a survey in the next class about what we would like to do, what you would like me to do. If we do not have to do linear algebra, then that frees some time for us, and we could do more things. I mean, the number of things that one can do is essentially infinite. You can go more in the direction of topology and do more topology. We did not do connectedness, how it interacts with continuous functions. We did not do that. We could do it, but again, it will be done in topology. Then all these norms, etc., on infinite dimensional vector spaces, we did not really see, but one can talk about spaces of functions and then perhaps do a little bit of functional analysis. That would be a cool thing to do if we have time left over at the end. How about quadratic forms? Were quadratic forms discussed?
That part was
okay. But I'm sort of hesitant to go too much in that direction because this is not an algebra class. I would love to do it, but we should do things that are more in the direction of what is in this course. Anyway, so today I don't really have anything. What we will do in the next class is we will now proceed just much more systematically. I will prove the equality of mixed partial derivatives, and then we will go towards Taylor's theorem. Both of those are pleasant and nice things. And once we have this, then the next thing is to do maxima and minima. For that, we will need a little bit of linear algebra. All of this should not take us a whole lot of time. By early to mid-April, we should be done with this. And then we come to something new, which in one variable situation is not really very much, which is the inverse function theorem and it's relative, the implicit function theorem, which are absolutely crucial for differential geometry. And once we do that, then our brief is sort of over. We have to do complex differentiation, which we will do. Sort of deliberately in the beginning, I did not say that the underlying field could be real or complex and try to do both at once, because after we do everything for real numbers, I will again have you do everything for complex numbers, because review the same concepts once again. Non-linear spaces, but that are complex vector spaces, and really the complex derivative, it's exhibits different phenomena. Complex analysis, holomorphic functions is a very different kind of thing compared to real analysis. We'll see a little bit. Anyway, so that is the plan. Are there any questions?
Sir, if we come during office hours, like, can we ask questions other than related
Absolutely,
stuff.
absolutely. So see what is happening during office hours is I'm not really getting anything. So in general, please do the following. See, sometimes I might even forget to you know turn on Zoom. But the best way to reach me is to call me. Unfortunately, I get many junk calls. So I may not pick up, right? But then the next thing to do is just send me an SMS saying that I'm a student, I'm trying to get in touch with you. I will call you back either right away or within a few minutes. Okay, that's the standard protocol. Call
Okay, sir.
me. If you don't reach me, send an SMS. I will get back. And during the office hours, I will get back right away because that time is designated for math questions.
Sir, I had a question about what we were doing in class today.
Yes.
I think I got confused at one part. When we were talking about like studying the second derivative in terms of partials, so the
Right.
function f, right? That was each component is a function from Rm to R, right?
Yes. Yes.
So shouldn't its partial with respect to?
Sorry, just 1 second.
Yes, sir. Yeah.
Let me just go up and let me see if I made a mistake. Won't be the first time. So this is what this is, right? So this is
Yes, sir.
right, huh?
Yeah.
Okay.
So del fi by del xk isn't. I might be getting confused. Isn't that a real number, sir, or a 1 cross 1?
Yeah, that is a real number. Yes.
So how are we taking the like?
No, sorry. Okay. Sorry. So yeah, no, that is a real. So it's the same thing. So when I take del fi by del xj evaluated at a, that's a real number.
Okay.
But when I let a vary, and I know that f prime now is a function. F prime is defined at every point. That means all those partial derivatives are also defined at every point. So when I let a vary, that again now becomes a real valued function on u.
Yes, sir. Yeah.
Correct. And again, now I can fix. So, okay, so this is right. So I really did not say it like this, and I should have. So tomorrow I will. Is that when I get this function, now this is a fresh function from u, a real valued function on u. So I can again take its fix any direction and take the derivative in that direction.
Yes, sir. Yeah.
Right.
Yeah, that makes sense, sir. Thank you.
And this sort of already begins to tell you how the question, this first green box, even though I'm saying f prime pq, I mean, what are the components of those f prime pq? I mean, they really are right. So you see, even though I have written it as question mark, it really is almost immediate because I'm thinking of it. So what I want to do is I want to take the function f prime and take its partial derivatives. But what is the function f prime? The function f prime in terms of its components is precisely del fi by del xk. Right?
I think I need to stare at it for a few more minutes,
Okay.
but I kind of do get it. So,
okay.
Yeah.
So, I mean, all I'm saying is that taking partial derivatives of a function which is vector valued, it's equivalent to just taking partial derivatives of each component function, right?
Yes, sir. Yeah.
And components of f prime are precisely the first partial derivatives of f.
Right.
So
Yeah.
It's just dictionary.
Yeah.
There is nothing to it.
Yeah, I see it, sir. Yeah. Thank you, sir.
Okay. All right. So somebody has something here. Yeah. So generally, by the way, you can call me anytime. If at other times I'm not, if I'm not free, I will just call you back. But this afternoon I will be free. Yeah. Yet another thing, by the way. And so part of the reason, so I understand that from my side, I should have, we should have started the homeworks at least, at least a couple of weeks before the midterm. And now we are the week after the midterm. One of the things is that I still want to make this document, of which I have a draft, which gives some kind of summary of the course or some short thing where you can just use that document in order to revise everything. And part of it is all the exercises that I give in class. So if somebody has a list of these exercises already typed up, if you can just send me the, if you have anything like that, and if you can just send me a simple text file, that will be useful for my compilation. Okay. I mean, just in case anybody has something of that nature.
Sir, I have some of them.
Yeah.
Some of
So
the more recent ones.
no, I mean, even if you have like 5 or 6, just a list, and you do not even have to send me the answers, just the questions, because for the midterm, I mean, that's sort of the practical thing, but just for yourself, what I'm thinking of is that if you, if I'm looking for like a list of just oral questions, by the end of the course, one should have maybe something like 50, of the order of 50 such questions. These questions need not be hard, by the way. In some sense, I do not like tricky questions or very difficult questions. Those are good to sort of get your creative juices going. But really, for basic understanding, one should be able to do the simple things, straightforward applications of theorems. But often, what happens is that you have something simple. It is too simple. And you say, okay, what theorems are applicable? The theorems are often very trivially applicable. Nonetheless, when you have an actual situation you are dealing with, you have to recognize what to apply among the various things that are proved. Like my teacher used to say, the way to prove things is to observe the obvious, but you have to observe it. Right? And it is a question of recognizing what it is that should be observed. So simple questions are good questions, especially when they are completely shorn of the context. You see, the moment an exercise comes at the end of a given chapter, it is not so good. And it is even worse when it is divided subsection wise in a book, because it already tells you what it is about. Whereas if you have a list of questions that are in random order about an entire course, then just getting your bearings right sometimes takes some time. So this is what I'm looking for, that the questions that I sort of see, many of these questions that we discuss, that I state in class, they are discussed in the next class, right? Often they are discussed. But to have a list of questions like this, fairly easy questions, but completely separated from their context, it's a good thing. Or at least this is what I think. So that's the kind of document that I'm trying to create, a sort of working, running document, which has a list of main topics. You just state some words and name some theorems, and one should be able to see that and say, okay, be able to tell what the definition is, tell exactly the statement of the theorem, give some examples, some counter examples, main idea of the proof, and a list of questions that you can use these questions for yourself. You can use these questions to quiz each other. And concretely, I can ask questions like this to you in the oral exam. It will not be difficult questions necessarily. But whatever I tell you, you should recognize what is relevant and what to apply. All right, anything else? Okay, so since there are only a subset of questions, what is the answer to the last question? What kind of maps?
Sir, I'm not sure if this is perfect, but it feels like we can just pick a basis of V, U, and W, and
Right.
sort of do this the exact same as above, but take A, B, and C to just be the set of bases, and then the map is generated from the basis.
Okay, excellent, very good. And that's a very good stepping point. All right, so let me just reword what you said. What you told me is that I can pick a basis of V, a basis of W, and on that basis, two things you are saying, one of which you said and one which I think you implied, is that if I'm given such a map on the basis of V cross basis of U, then I will be able to recreate the entire map. The answer is yes. The question is in what fashion? Okay. And the second thing which you implied is that can I really take this map on basis of V cross basis of U to be an arbitrary map, arbitrary set map? And will that give me a valid map that I want? What do you think?
I think it will, provided that we generate the rest of the map appropriately, and we do
Right.
that sort of linearly. So
Yes.
a linear combination should work out.
Yeah, right, exactly. So that the word linearly actually has to be understood properly, because there are two sets of linearities involved. You see there, L comes twice. So you're almost there, but the final word has to be there, that what kinds of maps from V cross U to W. And there is a one word answer to that. When you do this, you will recognize exactly what it is in light of what you have done in your linear algebra course, especially this semester. So good, let's stop, and then we will continue more systematically in the next class. Okay, good. All right, bye everyone.
Thank you, sir.
Thank you, sir.